happy always to collaborate and participate in this workshop and to give talks. It's a pleasure to be here. Actually, I should thank the organizer along the years, because in one of these workshops started one of my main collaborations now. So I invite you to talk during the coffee breaks, because it's always useful and you can have new ideas and start new collaborations. So today I will talk about something which is actually joined with Roberto Castorini, which is down there. And so basically, contrary to what you would expect, actually I will present one result, which is about thermodynamic formalism in dynamical systems, but I will not talk about thermodynamic formalism. So if you know it well, if you don't know it, don't worry, because you don't need to know it, basically. I will just spend most of the time to motivate it. So most of the talk will be just the main motivation, one of the main motivations behind our results, and has to do with anomalous transport, and in particular, you'll see about anomalous diffusion in dynamical systems.
But it's a complex system workshop. It works. Complex.
All'rovescio. Okay. Put it down. Go on. Okay, so what we mean about anomalous diffusion and transport. So we start with a random walk which is driven by a dynamical system. So you can think of having a dynamical system on your space X with a measure mu which is invariant and ergodic. And you can build your walks basically looking at the Birkhoff sums of some observable over the system. In particular, let me quickly make a picture here. I hope there is an eraser.
No.
Okay, so imagine the simple situation in which you have a unit interval. And okay, so imagine just a unit interval and think that your map is defined on a partition into two intervals. I'm not plotting the map for the moment, but you can imagine an observable which is equal to, for example, -1 when you are on the left interval and +1 when you're on the right. So if you build your sums with this observable, basically you will have a kind of random walk on the unit line, on the real line. And you can ask for the properties of this walk, in particular for the asymptotic properties of these sums. A very simple result, which is a very basic result, is about the strong law, right, for these sums, in particular the almost everywhere convergence for these sums. But here, this is a simple result, but we already see that there is something which is not always so simple. In particular, I didn't stress the fact that the mu should be a probability measure. There are situations in which the measure which you would like to look at can be an infinite measure. For example, this is typical if you want to look at some systems which can be models of physical systems in which the velocity is not bounded a priori, for example. In this case, the phase space is naturally infinite, and your invariant measure will be infinite. So anyway, in the simple situation in which the measure is just a probability one, and we always assume that our observables will be summable, so just take the simple case, then you know that almost everywhere, if you rescale the Birkhoff sums by n, asymptotically you convert the mean of your observable. Okay, so the almost everywhere behavior is quite simple. Already, for the almost everywhere behavior, if you look at the situation in which the measure now is infinite, something more difficult, of course, because in principle you don't know much about the asymptotic behavior of this sum. So this is already the difficulty which may appear. Today I will not look at the almost everywhere behavior, and anyway that's already some difficulties, but you can ask what happens when you look at other kinds of convergences. For example, you would like to look at the diffusions of the sums, right? So this is the standard question you can ask. And this is the example that I will consider during the talk, and because it's a family of maps, which maybe most of you already know, which is on this unit interval, may be considered into two intervals. It's just increasing, very simple one. Okay. The right branch is not very important. What is important here is that in the left branch, we have this fixed point here at 0, which is called indifferent in the sense that the derivative of the map at this point is equal to 1. And the statistical properties of the systems, and in particular of the Birkhoff sums of observables for this system, highly depend on the value of alpha. In particular, alpha will be our parameter greater or equal than 0. When alpha is equal to 0, you are in the very standard situation of the Bernoulli map, actually, when the derivative is not equal to 1, but equal to 2. So this is the very easy case. But when alpha is greater than 0, you are in this situation. And in particular, the measure for the system is finite if and only if alpha is less than 1. If alpha is greater or equal than 1, we are already in the situation of having an infinite measure. Anyway, you can ask, for example, for the standard convergence in distribution for our sums. And this is just a list of results that show how this convergence highly depends on the value of alpha. Something else, I will not concentrate on this kind of results, but for the same map, you can ask, for example, what happens to the moments of the sums. So this is the result that I will look at in particular. So we have some standard easy observable on the unit interval, and you can ask for the asymptotic behavior of the moments of the sum of the Birkhoff sums of this observable. And for example, one specific case in when q is equal to 1, so for example, the second moment, up to some, let's say, renormalization. If you assume, for example, that the mean of the observable is equal to 0, you basically look at this, at the behavior of these moments, and there is this kind of result, which is not actually a real result, at least not for this model. This is something which was shown by Roberto Artuso and Gianpaolo Pescatore in 2005 for a kind of easy model, which in some way is similar to this, that I call here the piecewise linear model. So our aim today actually will be to have an idea of how to find this kind of behavior for a general family of systems, for example, for this family. So this is the aim of the talk. And we will show how the thermodynamic formalism can work in making the proof, the idea of the proof by Artuso and Cristadoro, formal in all the situations that we want to study. So now I will spend some time just showing you the proof, the idea of the proof that they show in their paper. And in particular, highlighting what are the things that we know and what are the things that we don't know and we need to do. So what we know is, for example, that everything is quite easy when alpha is equal to 0. So when alpha is equal to 0, so the easy case in which actually you have the Bernoulli map, you have some good invariant probability measure, and if you can with a density h which is positive, and the idea is to look then, let's take an observable with 0 mean, and you want to look at this moment for the Birkhoff sum. So the basic idea is simply that this moment is nothing but the derivative with respect to this parameter beta of the moment generator function, right? Nothing more. And now you can take this quantity here and do just a very simple, let's say, way of rewriting this integral in the following way. You just take the terms which does not depend on t and take it on a side and just look at this term. Here you can write it just by composition with t. You take one of these t out of the sum, and then at this point you can do basically you can write this. So you're just reduced to the product of something which is just the Birkhoff sum of order n now, and this term where there is no t, no map. And then you basically do the simplest thing that you can do, that is just look at the dual operator. Okay? That is in many situations, for example, in the unit interval, just changing variables. You just change variable, and what you get is that you can take this t here, which is just a Human operator, basically, and transform it in what is called the transfer operator. This is just a change of variable operator, nothing more. And you reduce to this. So here you see the changing of variable, which is just the derivative of the map. The only thing that you have you have more than one pre-image for each point. So of course we have to consider all the different pre-images. And then you can go on. This is what was the first step. And then you can do, okay, you can do the same operation n times, big N times. And at the end, what you get is that the moment generator function can be written just by the application to the invariant density h of this operator, which depends on the parameter beta here. Okay, this is just a formal operation. And the point is that for the easy case in which alpha is equal to 0, we know a lot about these transfer operators. In particular, we can write it as a sum of a projection over the eigenfunction corresponding to the highest eigenvalue, plus something which is the rest, which is smaller in norm than this eigenvalue, the biggest eigenvalue, and this distance is bounded by some constant c. And this is true for beta small enough. Okay, so at the end we want to compute the derivative of beta with respect to beta and then evaluate it at beta equal to 0. So what we need to know is that everything works in a small neighborhood of 0. So this is fine, and then you can plug this equality of operator in your integral, and then you get this idea. So at the end, the asymptotic behavior of this derivative is nothing but the asymptotic behavior of the derivative of the largest eigenvalue of your operator. Very well, then if you want to be more careful, you can do some thermodynamic formalism by using another actor, which is the zeta function. Now, the zeta function is related to what we saw before, because it's a different way of highlighting what are the eigenvalues of your transfer operator. For example, if you look at this formulation here, if you substitute 1 here instead of this term, you get the standard Artin-Meson function with zeta function, which was introduced just to have a function which counts the number of fixed points and periodic points for a system. And you can generalize it by adding some weights along the periodic points, and in our case, by looking at some weights which depend on the observable f and on the parameter beta that you are considering. And basically, what is true is that you can need to believe me, for this simple case, the eigenvalue of the transfer operator to operator can be written as the inverse Laplace transform of this term, which depends on the zeta function. Everything is very nice because at the end, our moment of order 2q is nothing but the derivative with respect to beta of this term. Now the point is that in the situation in which Artuso and Cristadoro worked, they were able for these specific models to explicitly write down this zeta function. So this computation was explicit. The point is that this is basically impossible in general. So you need to find a way of justifying this behavior, right, for your systems. And this is true, so this is well justified only in our family when alpha is equal to 0, so when everything is expanded. Exactly the point is that when alpha is greater than 0, we don't know whether all this is true. So we have to justify a lot of things, but we have a lot of problems. And the problems are basically that the transfer operator is not quasi-compact, which means that there is no way of writing it as a projection over an eigenfunction plus something which is strictly smaller. It's impossible. And also there is a problem in taking the inverse Laplace transform of the zeta function because basically the two properties are strictly related. So if one is missing, the other should be missing as well. So basically we cannot do this step here. It's impossible to make this step. And also the eigenvalue here is not well defined. And here it comes the new idea that is to use induction. And the idea of induction comes from an older work paper that I wrote with Stefano Insola, where we did basically what we need to do now for a specific example, which is given by the Fari map and the Gauss map. So in red, you can see the graph of the Fari map, which is just basically one family of this, one map of this family, except for the part that this right branch now is decreasing. And if you construct the jump transformation of the Fari map by the standard operation, you get exactly the Gauss map, which is well known for its applications, for example, to regular continuous fractions. So what we did basically is to use the transfer operator of the two maps, and now I will not show you all the details. But the important thing is the following. So you can define a family of transfer operators for the Gauss map, which has the good properties of being expanding. And if you induce, starting from a map like this, you get something which is expanding everywhere. So you lose the problem of having different fixed points. So you construct this family, this power series of so these transfer operators valued power series, and at the end, what is important for us is that you get this kind of relation here between the zeta function of the Fari map and these terms here which have to do with the transfer operators of the Gauss map. In particular, the problems of the transfer of the zeta functions of the slope map, the one which is within different fixed points, is given just by this term here in front of these other terms, which depends only on the expanding and good map. So this was an easy case because the Fari map and the Gauss map have the good properties of having branches which are analytic, and so you can apply a lot of good, a lot of nice theories. For example, this is the well-known Fredholm determinant, which was studied by Grothendieck. So everything works very nice. So the problem that we faced with Roberto was exactly to try to do the same thing in a just simple differentiable case, when you don't have any analytic properties. And this is basically the framework that we studied, and you don't have to read it, just think of this family. It's written here. And for this family, basically what we did is exactly the same thing. So we proved that looking at the Jahn transformation, which is defined, the Gauss map is defined for the Fari map, at the end, we get this kind of results. So the zeta function of the slow map can be defined as a term which is based on the zeta function of the fast map, the G, which is expanding, times a term which only depends on the indifferent fixed point. So, just to come to the end, this is just a way of rewriting in terms of a new determinant. So what is interesting now is that how can we hope to apply this? This is work in progress. Then the hope is precisely to be able to write this term here, which was the one we wanted to control, by using this separation of the two problems. So we have something which only depends on the fixed point, and something which depends on the function which is expanding. Now the idea, the good news is that this term is explicit, and we can write it precisely what is the Laplace transform, is inverse Laplace transform. And this term is not explicit, but since the map is expanding, it should be regularly valued. So the idea is that we can control actually the inverse Laplace transform, since for good expanding maps you can do it. And hopefully we get then the results by opposing Christador.